introduced Professor Ryan O'Neill. He obtained his PhD in 2003 from MIT Mathematics Department, and he has belonged to the Computer Science Department at Carnegie Mellon University since 2006, where he is an associate professor with tenure. He received a lot of awards, including the NS Career Award and the Osaka Foundation Research Grants and the Alfred Sloan Research Fellowship and von Neumann Fellowship. And he's going to talk about the social choice, computational complexity, Gaussian geometry, and the Boolean functions. Please.
Okay, thanks. So I'm going to talk about the web of connections between these four topics here. In 45 minutes, it's not a lot of time, so I'll only be able to talk about the most basic aspects, but I encourage you to take a look at the survey that's on the archive that accompanies this talk for more details. And if you want even more details, you can see a whole book about the subject for free at this web address down here. By the way, I'm planning to not use the mic. If you're sitting in the back and you hear me, can you raise your hands? All right, great. At least most of the way to the back. So I'll start with the last topic, Boolean functions. So here's a picture. This is the discrete cube in n dimensions. It's all the vectors in Rn whose coordinates are plus or minus 1. And a Boolean function is just a map from the discrete cube also into plus or minus 1. In computer science, you think more typically you call bits 0 and 1 or true and false, but it's going to be more convenient for us to call them plus or minus 1. Sometimes, so f gives a labeling of plus or minus 1 to each point of the discrete cube. And sometimes it's also nice to think about a function geometrically. In particular, we'll look at it as an indicator function for all the points in the discrete cube that have value plus 1. Okay, so for the rest of this talk, I'll call the set of points where f is plus 1 S. So it's either a set of vertices or a Boolean function. The following random experiment for choosing two correlated points on the cube will be very important for us. It's called forming Rho correlated strings or inputs. Here, Rho is a parameter between 0 and 1. The way it works is as follows. For each coordinate I between 1 and n, with probability rho, we set xi and xi prime to be the same random bits, the same random plus or minus 1 value. So I denote that by a coin flip. And with the remaining probability for coordinate I, 1 minus rho, we set them to be independent random plus or minus 1 values. And we typically think of rho as being close to 1. So most of the time, xi and xi prime are going to be the same. And for a small fraction of the coordinates, they're going to be independent. So here's a little picture. It might look like this. See, most of the coordinates are the same and random. And then sometimes for these orange coordinates, they could be the same or they could be different. They're the same with probability a half. We like this parameter rho because it's set up so that the correlation between any column here, xi and xi prime, is exactly rho. With probability rho, the product is 1. And with probability 1 minus rho, the correlation is 0 because they're independent. So that's why we use the parameter rho. But let me also note, there's another way you can think about this experiment. If you just stare at x, actually just the distribution of x is uniformly random. Each coordinate is random. And then you can think of forming x prime by negating each coordinate of x sometimes. And the probability that xi prime differs from xi is exactly 1 minus rho over 2. Because for them to be different, first you definitely have to do this thing. And then when you flip independent coins, there's a half chance that they're different. So this 1 minus rho over 2 is an important parameter. The probability of the two coordinates are different. So this is a way of generating two points on the discrete cube, and let's look at the picture again. Let's say rho is 0.9. Okay? So then for 0.9 correlated strings, if you think about the second model, what happens is that the first input, x, is just a uniformly random vertex of the cube, maybe this one. And then you form x prime by negating each of its coordinates with 1 minus 0.9 over 2, which is 5% probability. Okay, so that'll sort of form a nearby points in the cube. If you think of n as being quite high or high dimensions, x and x prime will agree on about 95% of the coordinates, so some kind of nearby points. And what we're mainly interested in is what's the probability that this thing happens, namely that x and x prime have different values under f. Or in terms of the set S, the probability that x and x prime fall onto like different sides of S, one inside, one outside. So this is an important definition for us. The Rho sensitivity of f is just this probability, the probability that f of x differs from f of x prime when x and x prime are chosen to be Rho correlated vertices. And this is a kind of measure of a noisy boundary size measure for the set S, because you pick two kind of nearby points and look at the chance that they fall on opposite sides of S. So it's quite natural to consider the isoparametric problem that's associated to it, which set S has the smallest Rho sensitivity. And as always with isoparametric problems, it sort of only makes sense if you sort of fix the volume of the sets that you're talking about. Okay, and you can look at any volume, but the most interesting volume to focus on is a half. So it's most interesting or simplest to focus on sets S of half of the vertices of the discrete cube. One reason this plus or minus 1 notation is kind of cute is that if you remember F being the plus or minus 1 indicator of S, to say that the set S has half pluses and half minuses is to say that the expected value of F on a random vertex is 0. Okay, and we call F's balanced, such F's balanced. It's the same as the set S having fractional volume a half. Okay, so as I said, we're interested in this problem. We might call it the Rho isoparametric problem on the discrete cube, which balance function F minimizes the Rho sensitivity. Okay? This problem is actually not too hard to solve. It's got a well-known answer, which is a folklore result. But before I tell you about it, I want to start to talk a little bit about social choice, because this isoparametric problem on the discrete cube has a very natural interpretation in terms of voting. So social choice is the mathematical study of voting rules. So let's imagine you have an election in which there are n voters and 2 candidates, and the candidates are called plus or minus 1. So everybody votes, and we'll call xj the vote preference of the jth voter. And now what does a Boolean function represent? A Boolean function represents the voting rule, the method by which you take all the n votes and output who is the winner of the election. Now you might just think, well, you just take the majority of the votes, right? That's how we should have a vote. And indeed, that's one common and nice voting scheme. And another nice feature of this plus or minus 1 notation is that the majority of a bunch of votes x is just the sign of their sum. When we talk about majority, we'll always assume n is odd because ties are just an unimportant nuisance. But that's not the only voting scheme you can have. For example, it's kind of famous that in the United States they elect the president by this electoral college scheme where the n voters are broken up into 51 groups, and you take a majority within each of the groups, and then you take a weighted majority of the 51 outcomes. In fact, in many countries, the head of state gets elected in this way. My home country of Canada also elects the prime minister by a 2-level majority scheme. There's usually more than 2 candidates, though. So in fact, a Boolean function can define any kind of voting scheme. Okay, and in some overgeneralization sense, the mathematical theory of social choice is about comparing different voting schemes and their different properties. Here's another voting scheme which is commonly used in practice, unfortunately, just f of x equals plus 1. So everybody votes, but it doesn't matter, the winner has to be predetermined to be the candidate plus 1. We don't really like this scheme because it's not fair somehow. In particular, it's not balanced. Okay, so this is one reason we don't like it. It doesn't have an equal number of plus or minus 1. So we think like a minimally reasonable property of a fair voting rule is that it should be balanced, not inherently favoring plus or minus 1. So in the context of social choice, it's quite natural to only look at balanced functions. Oops. Okay, so in mathematical social choice, you need a model of how the voters vote. And for this talk, we'll talk about the simplest possible model introduced or named by Garman and Kamyan from Carnegie Mellon University in 1968. The impartial culture assumption, this just means that the voters' preferences are uniformly random. So it's a very simplistic model, but it's a nice one for comparing voting rules in the absence of any other information. So that's a standard assumption in social choice, and now I'm going to talk about a problem in social choice, one that involves like a non-standard assumption, which I'll call the twist or assumption of faulty voting machines. So imagine in the election, everybody goes to vote at the voting machines, and when a person enters their vote, it's recorded correctly with probability rho, and with probably 1 minus rho, the voting machine like silently malfunctions and just changes their vote to a random vote. And this is another reason why we hope that rho is close to 1. Okay, so in this scheme, you could see the original votes, x, which are like the true votes, granted they were chosen at random, are like this, and the faulty voting machines produce a new set of votes, which we may call the recorded votes, and they're exactly distributed in this rho-correlated inputs manner. Okay? And therefore, the Rho sensitivity, which is the probability f of x differs from f of x prime, is really the probability that the faulty voting machines affected the outcome, that the announced winner, f of x prime, differed from the true winner, f of x, or who was supposed to win, f of x. So therefore, it's natural if you're worried about guarding against faulty voting machines to try to look for the voting rule f, which minimizes this Rho sensitivity of f. Okay, so this brings us back to this problem, which has both a geometric interpretation on the cube and voting interpretation as well. Now, as I mentioned to you, the answer to this question is not too hard. It's a folklore result that dictatorship function f minimize this scheme. So if you really want to minimize the effect of the following voting machines, you should, I guess, use a dictatorship scheme. That's just one of the form f of x equals x sub j for some coordinate j. So everybody votes, but just whoever the j voters votes for is the winner. That doesn't seem too fair. We'll come back to it, but it is balanced because it's not inherently biased towards plus or minus 1. So it's kind of like half of Fox News. Balanced but not fair. Here's the geometric picture. So for a dictatorship, the set S is just a n-1 dimensional subcube. So in fact, there's n dictators, one for each kind of dimension. And it kind of makes sense that these are minimizers for this noisy boundary isoperimetry problem, because at least these sets S, all the points are kind of pushed together, so it looks like it might be minimizing a boundary size. So there are n minimizers here. Actually, there's two n minimizers. There's n more functions which minimize them, and guess Poe is flipping his hand. The negated dictatorships also equally minimize Rho sensitivity. That's a bit funny as a voting scheme. Just everybody votes, whatever the dictator says, you do the opposite. Kind of nice, maybe. So it's funny from the point of view of voting schemes, but geometrically it's kind of obvious. I mean, a negated dictator just looks like this. So by symmetry, it's the same. Okay, so another way to state this theorem is just as follows. It's restating the answer. For all balanced functions f, the Rho sensitivity of f is at least whatever it is for dictators. And what is it? Well, it's 1 minus rho over 2, because in our model, you see, the noise in the voting machines affects the outcome under dictatorship if and only if the dictator's vote gets reversed. And with the voting machines, each vote gets reversed with this probability. So this is the minimal Rho sensitivity of balanced functions f. The proof of this fact, as I said, it's fairly easy and it's a folklore result. It uses Fourier analysis of Boolean functions. And actually, I don't really know any other proof of this fact that uses a fundamentally different method. Okay, I want to take one more digression to talk about social choice. It'll take us a bit far away, but I couldn't resist talking about it. Imagine you have an election with n voters and 3 candidates called A, B, and C. And, oops, not only do you want to, you don't just want to elect a winner among A, B, and C, you in fact want to even rank A, B, and C. So the model is that every voter has a ranking, and you want to aggregate them into a societal ranking. Now, when there's 3 candidates, it's not quite so obvious what you should do. One suggestion made by Nicolas de Condorcet in the 1780s was to just reduce to the case of 2 candidate elections. Just hold an A versus B, a B versus C, and a C versus A election. And you can use majority or any Boolean function to hold each of these elections. This scheme subsequently became known as independence of irrelevant alternatives. So it's a good idea. Now there's a problem with it, as noted by Condorcet himself back in the 18th century. Even if you're using the majority scheme, it's quite possible that a majority of society prefers A to B, prefers B to C, and prefers C to A, which seems like sort of an impossible outcome, but it's an easy exercise to cook up an example where this happens. So that's a little bit too bad. Now, we talked on the earlier slides about potentially using different voting rules other than just majority, and you might think, well, maybe if I use a different 2-candidate voting rule besides majority, maybe electoral college or something, this unfortunate paradox will never happen. Unfortunately, it's essentially not possible, or it's possible only in an unfortunate way. This is a famous theorem due to Arrow's theorem from 1950. It was his PhD thesis, and it kind of kicked off the field of mathematical social choice, sort of with a negative result. He showed that it is possible to choose an f, which means these sort of impossible outcomes never occur, but only if f is a dictatorship function, or a negated dictatorship function. So, as I said, this started social choice off with a very negative result, an impossibility result, though these days we're not so worried about this as a negative result. Okay, so Arrow proved this theorem by some kind of combinatorial messing around, but in 2002, Gil Kalai gave a very beautiful, elegant new proof, which gave extra information about sort of robustness, and it used Fourier analysis, and it was exactly the same as the proof of, that I didn't show you, of the isoparametric problem about Rho sensitivity from the previous slide. Okay, so Kalai proved his results using Fourier analysis. Arrow proved it using some combinatorics. Actually, essentially for this result, Arrow was awarded the Nobel Prize in economics. If you haven't heard of the Nobel Prize before, it's kind of like a Fields Medal for other sciences. Okay, that's good. You laughed at the joke, so I'm going to give myself a check mark. That works. Oh, yeah. Is that pen? Highlighter. Okay, well, I couldn't do it in Korean. Sorry. Check. I hope this talk has a proof. Then it's going to be a great talk. We'll have to see. Okay, so let's go back to, we have these two kind of negative results. If we want to minimize the effect of faulty voting machines, or if you want to avoid Condorcet's paradox, the theorem tells us you should be a dictatorship. But we don't like that. It doesn't seem reasonable. And why don't we think it's reasonable? One reason is that in dictatorships, there's one voter that has an enormous influence on the outcome of the vote. So this is a very standard definition analysis of Boolean functions, actually invented originally independently by a geneticist and by a lawyer. The influence of the jth coordinate on F is just a probability in the voting scenario that the jth voter's vote is a swing vote. That if the jth voter changed their vote, it would change the value of the election. Or here's a mathematical way to write it. If you want to think about it geometrically, if let's say this is the function f, and this is the direction j, the jth influence is just a fraction of hypercube edges in that direction that have one endpoint in S and one endpoint outside S. So it's kind of the normal edge boundary of the set S in the jth direction. So as examples, in the dictator scheme, the dictator has influence 1, because if the dictator changes their vote, then certainly the outcome changes. And everybody else has influence 0. And that's one reason we don't like dictatorship, because there's one person with an enormous influence, the maximal influence, namely 1. On the other hand, if you take everybody's sort of favorite voting rule, majority, everybody has the same influence, and what's the probability that a particular voter's vote is a swing vote? Well, their vote is pivotal if and only if all the other n-1 votes exactly split 50-50. And it's well known that if you flip n-1 fair coins, the probability of getting exactly half heads and half tails is proportional to 1 over root n. And this we kind of like because, as n goes to infinity, this influence is going to 0. So it's saying that no one voter has like a non-negligible or very large impact on the outcome of the election, which seems like a reasonable thing to require for a fair voting rule. So in light of this, we can kind of change this Rho sensitivity isoparametric question, or this voting rule question, to kind of rule out dictatorships. We don't like them, so one might ask, suppose you wanted a balanced function f, voting rule, which minimizes the Rho sensitivity, but you don't want the dictatorships, or the anti-dictatorships, so you'll just insist that all of the influences be small. I'll make this a bit formal later. Then what is the best voting rule for minimizing the effect of the faulty voting machines? So this is a nice problem. It brings us to a very famous conjecture of the new Nevin-Luna Prize winner, Subhash Kote. I refer, of course, to this conjecture, the majority of stateless conjecture made with Kindler, Mossel, and me in 2004. And it basically says that the answer is majority. By the way, spoiler alert, we know the answer to this one. It's a theorem, so don't worry about it. Says that if f is a balanced function and all of the influences are smaller than some parameter delta, then the Rho sensitivity of f, it can't really be any smaller than that of majority. You can get smaller by some epsilon, but only an epsilon that goes to 0 as delta goes to 0. So that's the formal statement of the conjecture, also theorem. Actually, there's still one little problem. This doesn't quite make sense. The Rho sensitivity of majority is not just one function. It's actually a family of functions, one for each odd value of n. So what we really mean here is the limiting noise sensitivity of majority on n voters as n goes to infinity through the odd numbers. It's actually not obvious that this limit exists, but it does, and it's a very cute formula, cos inverse rho over pi. This was actually stated, maybe not exactly proved by Guilbeault in 52. Ken Arrow, after he proved his impossibility result, went around Europe talking about it, and Guilbeault saw his talk in Paris and wanted to compute the probability of Arrow's, Condorcet's paradox when you use majority. And as I said, when talking about collides, it's connected to the Rho sensitivity, and he worked out this formula. So we'll see the reason behind this formula later. But as I said, this is now a theorem, and this is what it says. So let me give you a plot to look at the parameters here. So on this plot, the horizontal axis is rho, which you can think of as like the quality of the voting machines. And the vertical axis is the Rho sensitivity, which is like the probability that the faulty voting machines affect the outcome of the election. And the dashed line is what you would get if you used the dictator scheme. You saw that the outcome would change with probability 1 minus rho over 2. That's a straight line. And this is what you get if you use majority for large n. That's really just the cosine wave if you tilt your head 90 degrees. And the majority of Stateless Theorem is saying that if you have any balanced function f, it's only possible to go below this solid yellow line the majority achieves if you have some voter in your scheme that has a really large influence. So basically, fair voting schemes cannot get below this yellow line. As I said before, we're mainly interested in the case where rho is close to 1. That's sort of the more sensible case. And actually, even without exactly worrying about these numbers, you see a qualitative difference here. This is linear, but we know that cosine is kind of quadratic at the peak here. So what that's saying is, even if the voting machines, say the voting machines are just reversing everybody's vote with some small probability epsilon, then under a dictator scheme, the result changes with probability epsilon. But with majority, it changes with probability like root epsilon, which is quite a bit bigger. And the majority of Stateless Theorem says you can't really do any better than that root epsilon. Okay. So this is majority of Stateless Theorem. It's from about 10 years ago now, and you might be wondering, why am I telling you this thing that's like a decade old? Well, one reason is that there's a very beautiful new proof of it from just last year by Day, Mossel, and Niemann. And I'll talk a little bit about it at the end of the talk. And we'll in fact see that, not is it just aesthetically pleasing that there's a new proof. It's actually important mathematically to have a different kind of proof of this theorem than the original proof. Now, let's go back to the 2004 paper that made this conjecture. Subhash and Guy and Elkanah and me were originally not really interested in voting. We're theoretical computer scientists. So why do we make this conjecture about the most stable voting rule? Well, if you saw Subhash's talk, you know that, sort of amazingly enough, this majority is stablest fact about voting schemes is like literally exactly the statement you need to prove in order to show an optimal computational complexity result for an algorithmic task called max cut, which in fact Subhash talked about. So I want to take a brief digression now into the topic of computational complexity, which is also mentioned in the title, and remind you a little bit about this max cut problem. Okay, so briefly, the max cut problem is an algorithms problem. The input is any old graph on n vertices, but you should think about it as being an almost bipartite graph. Now, if you look at this graph, it doesn't obviously look like it's almost bipartite, but actually it is. I mean, if you just move the vertices so they look like this, sorry I was unable to animate the edges, but these are actually the same graph, and you make a bipartition, you see it's almost bipartite, except for these two yellow edges, which I'll call mistake edges. All of the edges go between the two parts. Okay, and the task in max cut is, given the graph, find the bipartition which has the fewest mistake edges. Okay, this is the sort of simplest example of a constraint satisfaction problem, really, if you saw Andrei Bulatov's talk. Okay, so what do we know about this problem? Well, we want to solve it by a computer algorithm. The simplest possible algorithm is just enumerate all bipartitions, of which there are 2 to the n, and then pick the one with the fewest mistake edges. Well, that works, but it takes about 2 to the n steps or more, and so you cannot even run it on a graph with like 40 vertices. So this is an unsatisfactory solution. The thing that you really look for usually is a so-called efficient algorithm, or an algorithm that solves the problem whose number of steps it takes scales as a polynomial, some n squared or n cubed or something, in the number of vertices of the graph. So that's the question, is there an efficient algorithm to solve this max cut problem? The answer to this question is no, so that's kind of disappointing. Well, technically it's no, assuming that P does not equal NP conjecture, which is a very famous mathematical conjecture that everybody believes in. It's kind of like the Riemann hypothesis of theoretical computer science. So, the formal way to state this fact is that the max-cut problem is NP hard. This is a very old result, and it simply says that there is no efficient algorithm for the problem unless P equals NP, which nobody really believes. Okay, so that's too bad. But as Julia was saying in her talk, you're sitting there with the graph. You still want to try to get like a bipartition, and you want to run efficiently. So what are you going to do? Well, what you can try to do is, solve the approximate max-cut problem. So it's the same situation. You're given the graph. You have to efficiently output some bipartition, and you're just trying to, do the best you can. Try to have the smallest fraction of mistake edges that you can in your bipartition. Okay. So there's a very famous theorem about this problem. There's an efficient algorithm which was essentially proposed by Delorme and Poljak in '90. It's efficient due to work of Rochel, Lohaus, and Schreiber from 1988. But Gomez and Williamson were the people who really analyzed this algorithm, so it's usually named after them. It says the following. This algorithm, if you give it a graph which is row bipartite, I'll say what that means in a second, then the algorithm is guaranteed to output a bipartition where the fraction of edges which are mistake edges, they stay inside the bipartition, is at most this memorable quantity, inverse cos of rho over pi. Okay, so what does rho bipartite mean? Well, a 1 bipartite graph just means a bipartite graph. A 0.9 bipartite graph means a graph where the optimal bipartition has 5% mistake edges. And in general, the definition, I'll say, of a rho bipartite graph is one where the optimal bipartition has at most a 1 minus rho over 2 fraction of mistake edges. Okay, so now if you look at these two quantities in yellow, they look very familiar, I hope. I could draw a picture of the performance guarantee of the Gomez-Williamson algorithm. Actually, I have to briefly mention that this theorem is slightly not true as stated. It's only true when rho is bigger than this number 0.69, which is like some funny number, cos alpha pi, where alpha is the root of tan alpha over 2 equals alpha. The situation when rho is less than 0.69 is also well understood, but it's a little bit more complicated. So let me just focus on this case. In any case, we're mainly interested in rho close to 1. So here's the picture. Sort of the same picture. On the horizontal axis, rho, it's like how bipartite is the input graph, ranging from totally bipartite to this, like the complete graph would be over here. And the vertical axis is the fraction of mistake edges. So here, the dashed line represents the fraction of mistake edges in the optimal bipartition, just by definition of what 1 minus rho bipartite means. And the solid yellow line is what Gomez-Williamson algorithm guarantees you. They guarantee you a bipartition which has this fraction of mistake edges. And it turns not solid here at this 0.69 thing. Okay? So this is quite a good algorithm. One good thing about it is that if you have an almost bipartite graph, it finds you an almost bipartition. One bad thing, though, is there's still this qualitative difference between, the linear behavior here and the quadratic behavior here, but it is what it is. And in fact, it's much, much better than the previous best efficient algorithm, which had the property that if you gave it a bipartite graph, then fine, it would find a perfect bipartition. Otherwise, if the graph is not bipartite, it would basically give you junk. So this was a very impressive algorithmic result. Okay, so the main theorem in this paper from 2004 was an implication. The main theorem was the implication that if the majority of stateless fact is true, which turns out it is, then it's NP hard to beat the Gomez-Williamson max-cut algorithm guarantee. Okay, so you cannot get underneath this yellow line with any efficient algorithm. Actually, that's a little bit of a lie. It's not NP hard, it's merely UG hard, which means that it's hard assuming Subashko's unique games conjecture. So you heard a lot about that. I won't get into it anymore, but it's some kind of evidence that doing better than the Gomez-Williamson algorithm is hard for efficient algorithms. Okay, so unfortunately I don't have any time to tell you about why this voting problem has anything to do with the hardness of max-cut algorithms, but that's a nice fact. I should also just mention one more thing. This is not some kind of one-off result about max-cut. It fits into a general theory that was developed among other people by Austrian, and then the main result was Raghavendra's PhD thesis, where you showed basically the same result for every constraint satisfaction problem. That there's a certain generic efficient algorithm A, and however much it achieves, for an approximation ratio, it's usually hard to do better than that. And it follows by sort of generalizing all this majority of stablest business and this implication from this theorem. Okay. So that's a taste of what the relevance of this voting problem or voting theorem majority of stablest has for computational complexity. And now I'd like to spend the last 15 minutes of the talk talking about how to prove the majority of stablest theorem. And this is where the last topic in the title enters the talk, is Gaussian geometry. Okay, so let me just quickly remind you, in case you forgot, what is this majority of stablest theorem, whose proof we'll talk about. You have a balanced function on the Boolean cube. Think about it as the indicator of a subset of vertices S. And for rho correlated inputs x and x prime, what that means is x is a uniformly random point, and then x prime is formed by negating each of its coordinates with this probability 1 minus rho over 2. So that finds some nearby point x prime, and the rho sensitivity of f is the probability that f has different values here, so that one is in the set S and one is outside the set S. And the majority of stablest theorem says that if you have such a function and it's not so much like a dictator in the sense that all of the influences are small, then the rho sensitivity cannot be much more than this cos inverse rho over pi, which is the limiting rho sensitivity of the majority function. So this is what we want to prove. And in talking about proofs or how to prove it, it's actually a little bit important to see where this formula comes from. So let me try to talk about that now. So what is the rho sensitivity of the majority function on n bits? Well, by definition, it's the probability that majority of x differs from majority of x prime for rho correlated inputs. And as we saw before, you can express the majority like this way, the sign of the sum of the coordinates. Now, the sign of a number doesn't change if you divide by some positive number, so let's divide by root n inside both the signs. And now you see, for example, x is a random vector whose coordinates are plus or minus 1, 50, 50 each. If you add them up and divide by root n, what you're going to get is a random variable that's pretty much like a Gaussian. And similarly, x prime is also a uniformly random plus or minus 1 vector, so this will also be like a Gaussian random variable. But they won't be independent Gaussians because x and x prime are correlated. In fact, if you use some two-dimensional central limit theorem, you'll get that this probability converges to the probability that the sign of z differs from the sign of z prime, where z and z prime are standard Gaussians which are themselves rho correlated, which just means they're jointly normal, standard normals with covariance equal to rho. Okay, so that means to evaluate this rho sensitivity of majority in the limit, you just have to figure out this Gaussian, this two-dimensional Gaussian probability. And at this point, you can kind of figure, well, it's some kind of calculation. I'm sure I can do it. Actually, it turns out you don't even need to calculate it at all. It's a very simple exercise. Let me just get to this part. To show that it's exactly this cos inverse rho over pi. So this was so easy that Shepard proved it in 1899, and you can also try it yourself. Just going back a little. Another way to think about this experiment is, here's the real line. And this should be down here. Something happened with the picture. Here's the set S, the positive half line. And the sine function is like the indicator function of this positive half line S. Okay? And what happens is you pick two correlated Gaussians, z and z prime, in this experiment, and you look at the probability that one falls into that positive half line and one doesn't fall into the positive half line. So that looks a little bit familiar. What we really see from this example, what you should take away from it, is that the n-dimensional Boolean function majority is nothing more than like the one-dimensional Gaussian function sine, SGN sine, in disguise somehow. And in fact, this quantity up here, let's give it a name. We can define this quantity to be sort of the Gaussian rho sensitivity of the one-dimensional sine function. The sine function maps R1 into plus or minus 1. Its indicator is the positive half line. And we're doing a similar kind of experiment to the normal rho sensitivity. Just to make it look even a little bit more familiar, see this positive half line here has a Gaussian volume of half. A random Gaussian is inside the positive half line with probability of half. In other words, sine is balanced as a Gaussian function. Its Gaussian expectation is 0. We can generalize this idea of, the majority function being the disguised version of the sine function. Let's suppose you have a function on d-dimensional Gaussian space, G, mapping it into plus or minus 1, the indicator of some subset of Gaussian space of volume F. Well, it could be of any volume. We'll define the Gaussian Rho sensitivity of G to be the probability that G of Z differs from G of Z prime, where Z and Z prime are Rho correlated standard Gaussian vectors in d dimensions. So you can read the formal definition here if you like, what Rho correlated standard Gaussian vectors are. And the moral here is that if you have any Gaussian function G in d dimensions, you can disguise it into a sequence of small influence Boolean functions. How does that work? Let's do an example where d equals 2. So here's R2. Here's a set S in R2, this disk. So you should think of G as the function on R2, which is plus 1 on the disk and minus 1 off the disk. And here's how you disguise it. Actually, for each value of n, we're going to make a Boolean function on 2n coordinates. And to get f on x1 through x2n, these are plus or minus 1 values, just add up the first n values, divide by root n, add up the second n values, divide by root n, and plug these two numbers into G. So this kind of defines a Boolean version of this Gaussian function G on many inputs. And there's some very interesting properties you can check here. So as n goes to infinity, this really gives you a family of Boolean functions. First of all, by sort of the same central limit idea, these are going to act like correlated Gaussians. You can show that the Rho sensitivity of this family of functions, Boolean functions f, tends to the Gaussian Rho sensitivity of G. Similarly, you can check that if G is balanced in the Gaussian sense, f will tend to a balanced function in the Boolean sense. In both cases, 50% chance it's plus, 50% chance it's minus. And finally, it's not hard to see that the influences of all the coordinates on f are something like 1 over root n. In particular, they go to 0 as n goes to infinity. So as you make n bigger and bigger, all the influences on this function tend to 0. And if you remember, these two conditions down here, balancedness and small influences, are exactly the hypotheses of this majority of Stateless theorem. So what does this mean? So let's think carefully about this point. You have some function, Gaussian function G. You can produce this family of essentially balanced and small influence functions f. Now, if you believe the majority of Stateless theorem, you could apply it to all these functions f and conclude that their Boolean Rho sensitivity can essentially not be any smaller than this cos-inverse rho over pi. It's that minus a little bit depending on the influences, but you can make that little bit go to 0 just by taking n to infinity. But the Rho sensitivity of f also goes to the Gaussian Rho sensitivity of G. So what that means is, if you believe the majority of Stateless theorem, which it is true, it implies by this relatively simple construction this fact, that if G is a balanced Gaussian function, its Rho sensitivity, Gaussian Rho sensitivity, has to be at least this cos inverse pi over rho. Exactly. This, by the way, is achieved by the sine function in one dimension. This is actually a geometric theorem. Let me just state the exact same fact, but geometrically it says that if S is any subset of d-dimensional Gaussian space of Gaussian volume a half, you pick two Rho correlated Gaussian vectors, the probability that they're on opposite sides of S, one inside, one outside, is at least cos inverse rho over pi. And again, you see it's like a geometric isoparametric theorem about sets S, because this probability here, the probability that these two random vectors fall on opposite sides of S, is some kind of, again, fuzzy measure of the boundary size of the set S. So if you want to prove this majority of Stateless theorem, you have to at least be able to prove this special case, which looks like quite an interesting special case concerning Gaussian geometry. Luckily, this special case was proved by Borel in 1985. In fact, Borel proved significantly stronger results than this, but in particular he proved this thing. I should mention that this equality is achieved not just by the half line in one dimension, but by rotational symmetry of Gaussians. It's actually achieved by any half space S through the origin. Great. By the way, this Borel isoparametric inequality is quite powerful. If you take rho close to going to 1, that's like taking these correlated random vectors z and z prime to be very close to each other. It eventually measures literally the normal Gaussian surface area of the set S, the integral of the Gaussian PDF over the surface. So you can actually deduce from this the classical Gaussian isoparametric inequality. Okay, so as we've seen now, the majority of stateless theorem implies the Borel isoparametric inequality, the statement about geometric isoparametry in Gaussian space. So if you want to prove this statement, you better prove this statement. So let's talk about the proof of Borel's isoparametric inequality. And here I'm going to get into a little theme for the last part of the talk, which is the importance of having more than one proof of a fact. So actually, I know of 5 different proofs of this Borel isoparametric inequality. 5.5 maybe. The first one is the one by Borel from 1985. It uses Gaussian rearrangement technique. And I must say, I hope Borel is not here in the audience. So actually, I hope he is here in the audience. But the paper is very hard. I tried to read it like 10 times, and I never managed to successfully read it. I guess that's my failing. Well, the other proofs I understand a little bit better. So in 1990, Beckner pointed out that it's actually possible to get a simpler proof if you try to prove a harder statement, a more general statement. So Beckner considered the analogous sort of noisy isoparametric problem on the surface of the sphere. On one hand, it's actually pretty easy to show, find the solution to that problem using 2-point symmetrization. And furthermore, it's kind of well known that you can deduce facts about Gaussian geometry if you prove facts about geometry on the surface of the sphere by sort of taking a limit as the dimensions of the sphere goes to infinity. So some of the details of that limiting argument were worked out by Carlin and Loss in 1990. Okay, flash forward, there weren't too many new proofs for a while. Now in 2012, me and Guy Kindler gave a new proof. Now it only works in the case of sets of Gaussian volume 1/2, which is actually all we care about for majority of stateless. Borel actually proved the correct isoparametric inequality for sets of any fixed volume. Our proof only worked for sets of volume 1/2. And it only worked for certain values of rho. It only worked if the rho was cos of pi over an integer. Which actually isn't so bad, because by taking that integer very large, pi over that integer goes to 0, and the cosine goes to 1. So we at least get it for a sequence of rows that tend to 1. And rho tending to 1 is kind of the main interesting case. Anyway, if you only care about these 2 special cases, then you can prove this inequality in 4 sentences. You can check it in the proceedings version. So it's a very simple proof. Okay, so I have like 2 or 3 minutes left. You know, it's such a simple proof, it's 4 sentences long. I thought I might show it to you, but I think I don't even have time for that. So I got the joke, but I guess I should put an X on this proof. This was a 50% successful talk, I guess. Okay. So I won't show you any of these proofs, unfortunately. Actually, this is the time for me to remark about the first proof of the majority of stateless theorem. So we proved that in 2005. The way we did it was by reversing this implication. So one of the main technical parts there was proving something called an invariance principle, which is some sort of nonlinear generalization of the central limit theorem. And once you prove this, you're actually able to reduce the majority of stateless problem, which is about discrete things, plus or minus 1 random variables. You can actually reduce it to the Gaussian special case, namely Borel's isoparametric inequality. And then luckily we have at this point a couple of different proofs of the Borel isoparametric inequality. And that's how we derive the majority of stateless theorem and its consequences about computational complexity. Okay, so in some sense that ends the story of how to prove majority is stateless, but I want to go on because I'll get to talk about a different proof of majority is stateless this way. So let me actually go back to the 5 or so different proofs of the Gaussian statement, the Borel isoparametric inequality. So in 2012, Mossel and Niemann gave a very slick proof using what's called the semi-group method. And in turn, this directly inspired 1 year later a paper with Anindya Day, which gave a totally new proof of the majority of stateless theorem, a completely discrete proof. It's a statement about n-dimensional Boolean functions, and they proved it by proving a statement by induction on n, which is very elegant. And since we know we have this implication, it gives also a new proof of Borel's isoparametric inequality. Finally, I should mention, also in 2013, Eldan gave a proof using stochastic calculus, which gives more information about the cases of near equality. Okay, so this is my last slide, and it's about the importance of multiple proofs. So now there's 2 proofs of the majority of stateless theorem. The first one, the original one by Mu, used invariance principle to reduce the problem to something about Gaussian geometry. One advantage of this proof is that the tools, the invariance principle, for example, is useful elsewhere in social choice, learning theory, other areas of computational complexity. And in particular, so far as we know, you need this whole invariance principle approach to get this Rogavendra theory of optimal approximation algorithms for all constraint satisfaction problems. On the other hand, the De-Mossel-Neiman proof of majority is stateless from a year ago also has its advantages. As I said, it's a direct induction on n. It's completely discrete, so it's very aesthetically pleasing and elegant that we have a discrete proof as befitting of a discrete theorem. But it has one more intriguing advantage, which you may understand if you saw Boaz Barak's talk or if you're going to see Monique Laurent's talk. The proof is kind of simple enough and elementary enough that you can express it in a limited proof system. You can express it using the so-called sum of squares proof system. And that's a significant portion of their paper showing how to fit their new proof into this framework. And the very fact that you can prove this fact in a limited proof system actually has some intriguing algorithmic implications, as it turns out, for the computational complexity of the max cut problem and for the unique games problem itself. Thank you.
Any questions? No comments?
I have a silly question. So what was this number 0.8 in the laudation?
Yeah, that number in the 0.8 in the laudation, it's something slightly more complicated than the ratio. I don't know if I can get to this. It's something slightly more complicated than the ratio of this number to this number, like the biggest ratio between this curve and this curve. Actually, it's the ratio of the difference of this curve from 1 and the difference of this curve from 1, for some, in my opinion, funny historical reason.
Any other questions? No more questions?
What's the belief about the truth of the unique games conjecture?
Yeah, I'll say this anecdote. So we learned that Subhash was winning the Nevin Lino Prize, and we were at lunch, me and some other theoretical computer scientists, and Sanjeev Arora, who gave the laudation. And we took a poll, how many of the 5 of us believed it, and I was the only one who voted in favor of it. Actually, it's better if it's false, because if it's false, it means we have some amazing new algorithm that we can use for many great new things. If it turns out to be true, it just means it's sort of case closed on a lot of problems. But in addition to this, as Subhash likes to say, it doesn't really matter so much if it's true or false. I mean, as it turned out, it generated so many interesting directions, and for example, theorems that have nothing to do with its truth or falsity. That it's a great question, regardless of its truth value.
Any other questions? No more questions? Then let's thank our speaker again. This is